This is Niels Bohr. He was a brilliant Danish physicist who made foundational contributions to understanding atomic structure and quantum theory, and he won the Nobel Prize in 1922. But that doesn't mean he was right. Now, the Bohr model is essentially what we talked about last class. That's the one where we get this diagram where we've got a series of energy levels, right? So we've got the hydrogen atom, and we're saying that the hydrogen atom can be in any one of these states. Specifically, the electron of the hydrogen atom can be in any one of these states. And if the electron absorbs energy, well, then it must absorb exactly the amount of energy to go from one of these states up to one of the others. And if this electron emits energy, well, then it must have started at one of these higher energy states and have fallen down to one of the states below. And consequently, it will give off a photon of exactly that energy difference. Now remember, there could be more states, and there are more states above number 4. We're just sort of drawing a simplistic model here. Now, the problem with this approach is that the evidence we collect to support it is actually not enough so far to refute the possibility of there being more states. Let me explain. What if, and this at this point is just sort of an odd conjecture, but what if at the n equals 2 level there were actually, say, 4 states? Would that make any difference? Well, insofar as we've studied this problem so far, I would say probably not. Because, again, so long as all of these states happen to be at exactly that same energy, my electron could be in any one of them, and as long as it drops back down to the ground state, it will have changed by exactly that same amount of energy, regardless of which one of these n equals 2 states it falls from. So if I see a photon emitted from this system that corresponds to this transition from the n equals 2 state down to the n equals 1 state, I know there's a state that is most definitely at that energy, but I don't know how many states are actually at that energy, and there could be many. I'm proposing 4 here in a way that's maybe a little bit of foreshadowing. So there might be more complexity hidden within this diagram than we initially thought last class. And so really there's nothing at this point stopping me from proposing the same thing for all of the other states. In fact, what if I proposed that there were 9 states at the n equals 3 level? What if I proposed that there were 16 states at the n equals 4 level? So for all we know, there's nothing preventing this particular diagram from being true. All right, so how are we going to figure this out? Well, really the key comes from thinking about systems that are more complicated than the hydrogen atom. You see, Niels Bohr was essentially famous for introducing this quantum model, specifically with respect to hydrogen. And the reason why hydrogen is a somewhat simplistic case is that hydrogen only has 1 electron. And if we are outlining here different states, different energetic states that electron can be in, well, the picture is a little bit simpler than it would be if we had many electrons. Even just a helium atom with 2 electrons all of a sudden has 2 different electrons, and therefore 2 different states that could be populated at any time, and those 2 electrons will likewise repel each other and therefore affect each other's energy, and the system is far more complicated that way. So in fact, if we were to recall the equation that we spent a bit of time learning last class, in other words, the change in energy between any two states represented as minus hcr times 1 over nf squared minus 1 over ni squared. We used this equation last class to predict the precise difference between any two states, and it turns out that this equation actually completely breaks down for any system other than hydrogen. So as soon as we start to add more and more electrons, this equation just doesn't work anymore and isn't able to predict those barcodes we talked about last class. It isn't able to predict which photons will be emitted from a particular element. Really, hydrogen is the only one it's good for. And so, for this reason and several others, the Bohr model is patently false. It's not something to be believed in modern chemistry, but it was very foundational in terms of bringing our understanding out of the old classical sort of continuous energy model and into the new idea of energy being quantized and electrons actually existing in states. Okay, and so that is really the fundamental discussion I want to have today, and that is, let's see if we can, expand on this original Bohr idea and understand really how many states do we actually have available to us, and what do those states actually mean. That's the point of today. Okay, so let's do this change. Here is the Bohr diagram, the one that we're a little bit skeptical of at the moment. And we have Erwin Schrödinger to thank. Maybe you've not heard of that name before, but it's just as famous. Just as many Nobel Prizes went to Schrödinger as to Bohr. And it was Schrödinger who took Bohr's ideas that much further into the realm of really thinking about many electrons at the same time. And that's really the key. And it was Schrödinger who wrapped mathematics around all of this in a more general way that could predict how many energy states there should be and what the distribution of those states were. And Bohr wasn't all that far off, but let's talk about it here. Bohr had essentially one state for every energy, and they were labeled with this n value, right? N equals 1, n equals 2, n equals 3. And this n value is what we come to know as the principal quantum number. Okay, so that's what Bohr taught us. But of course, we actually need more information to describe real chemical systems. And Schrödinger's approach expanded on Bohr's model in what is essentially the following way. Now, I'm not showing the n equals 4 level, simply because I would need to draw too many lines. It would be off the sheet of the page. Now, how many lines would I have to draw, right? How many states would there be there? Well, what I want to show you is the incredible and frankly beautiful patterns that have evolved in these systems. And remember, these are inanimate particles. I mean, these are electrons. These are negatively charged particles orbiting a positively charged nucleus. And there is an amazing series of patterns that unfold in the behaviors of these particles that I want to expose you to today. And these come out of Schrödinger's math. Okay, so Schrödinger works out these math. And so if you're asking yourself, like I would encourage you to always ask, what is the evidence? Why should I believe Schrödinger? Well, it goes in the opposite direction. Bohr we believed because he could predict the hydrogen spectrum, the barcode that we saw coming out of the discharge tube. But then we discovered that his math didn't predict any of the other barcodes. It's Schrödinger's math that predicts all of the other barcodes. And so it was nice that Schrödinger's model kind of looked like Bohr in some sense, but it was far more expansive, far more descriptive, and frankly, as far as we know, perfectly accurate, and it is a beautiful model of matter. I want to explain it to you today. Okay, so this is what Schrodinger's model predicts. So if I go from the n equals 1 to the n equals 2 to the n equals 3, where Bohr would have had just 3 states, say maybe this one, and this one, Schrodinger has many states. Okay, so let's start talking about these. And then we're going to give labels to all of these states so that you can understand what it is I'm talking to. If I point to this state, can you give that a label? But then we're going to talk about contextually, what do these states actually mean? What do they signify? If my electron is in those states, what is it doing? And those are the kinds of questions I want to tease out today because they're important. Okay, so we've got this principal quantum number. Schrodinger didn't throw that away. We still have this n equals 1, n equals 2, n equals 3. The problem, though, is with the exception of this n equals 1 state, all of the others seem to describe many states. So if I say n equals 2, if I were to tell you that I have an electron that has absorbed energy and it has been excited to the n equals 2 state, the problem is you don't know which one it's in. You don't know which of these 4 it's actually in. So this is something we need to resolve today. And likewise, the problem only gets worse as we go to n equals 3. Now you've got 9 states to figure out there. And this is the first piece of the pattern. Notice there is 1 state at n equals 1. There are 4 states at n equals 2. There are 9 states at n equals 3. If you have not seen the pattern yet, let me be abundantly clear, there is an n squared pattern here. And the interesting thing is that this n squared pattern continues to infinity. Anyway, what I mean here is that if my n value is 1, n squared is 1. There is 1 state at the n equals 1 level. If my n is equal to 2, 2 squared is 4. There are 4 states at the n equals 2 level. If my n squared is 3, you guessed it, 3 squared is 9. There are 9 states at this n equals 3 level. So the first question I'd asked before was how many states would I have drawn up here at the n equals 4 level had I had enough space on my iPad to do that? Well, I'm hoping that you would guess that if n is equal to 4, 4 squared is 16. I would have actually had 16 states written up here, and frankly, I just don't have enough room. Okay, so there's the first pattern I want to explain to you. There are n squared states for every n level, right? And then that continues. And this is, I'm starting to get excited because these patterns turn out to be beautiful and amazing, and I've only just got to the tip of the iceberg. So let's start thinking about this. So there's the first pattern. There are those many states for each of these n levels, okay, n squared. Now, you'll notice I've also partitioned them somewhat. Notice there's a bit of a space here. Notice there's a bit of a space here and a space here. I've done that very intentionally. I have spaced out or otherwise somehow differentiated the new states every time I go up, right? So I started with 1. And now as I go up to the n equals 2 level, let's just leave that 1 there. I could have that 1. But then I have 3 new ones. And so I've written these off to the side a little bit just to differentiate them. And then as I go up to the n equals 3 state, same sort of thing. I've just sort of kept those original 4, but then I added 5 more. Okay? And again, I've just added these 5 just off to the side of the original 4, just to signify to us that those are the new ones now that we've gotten to this particular state. And this is not so different than the n squared relationship I was talking about before, but we always add an odd number of states. Okay, so we started with 1. We add the next odd number, which is 3. And so we've added 3 states. The next odd number past 3 is 5, and so we've added 5 states, so on and so forth. And so the very next one would be, of course, 7. I would add 7 more in addition to these 9 up into the n equals 4 level. And of course, 7 plus 9, 16, right? 4 squared. All right. So talking about it in this way describes these sets of states as being distinct, the new ones that have been added. And so what we can do is we can start to give these states labels. Okay, and that's the first thing I want to do today. I want to give these different sets of states labels. Now what I'm going to do is I am going to label the original one, right, that original one, and I'm actually going to label all of these types of states with something known as an L value. Okay, I'm writing my L as sort of a lowercase cursive L almost. And these other sets of states that I've written here, I'm going to give them an L value. Now, I've already given them an N value, right? So this state has an N value of 1. All 4 of these states have an N value of 2. All 9 of these states have an N value of 3, so on and so forth. But I want to actually get a little bit more specific, and I'm going to also give them L values. This is another quantum number, right? It's another quantum number that is going to help us define which one of these states I'm actually in. Okay, so that's something that I want to keep track of here. All right, this new quantum number is going to be called the angular momentum quantum number, sometimes also called the azimuthal quantum number. But nonetheless, it's just a number. It's just a descriptor of all of these different states. And what I'm going to do is I'm going to say that this first state here has a number of 0. And in fact, what I mean here is that all of the first states have a number associated them with which is 0. Okay, now we don't need to be concerned about why is that number 0. Really all we're trying to do here today is label these, okay? And so we can just accept any arbitrary label as long as they're labeled. And now what I'm going to do is I'm going to name the additional sets that get added every time with an increment on L. So L started at 0. What's the next number? The next number is 1. So what I'm going to do is I'm going to label this next set, right, the new set that got added, as an L value of 1. And so I'm going to continue to do that all the way up. And it's probably not a big surprise that this next set that gets described over here, I'm going to increment L yet again. And so now this is an L value of 2. And again, I just want to stress the point here is really only to assign labels. Okay, so at first I had a label of n equals 1, and then I had a set that was labeled as n equals 2, and another set that was labeled as n equals 3. And now what I'm doing is I'm just adding some sub-labels, some inner nested labels that will specifically identify those new sets of states that have been added each rung of the ladder here, each time I go up. Okay, so now I have a second quantum number, L, which again is called the angular momentum quantum number, or otherwise known as the azimuthal quantum number. Okay, so that's that one. Unfortunately, we're not quite done because we're not actually specific enough. Notice that in this particular set of states here, if I'm going to be explicit with my labels, my n equals 3, L equals 2 set, this set of 5 right here, it is a set of 5. I don't know which one of those 5 I'm talking about if I give you that number 3 and that number 2. I still have to be a little bit more specific. So what we're going to do is we're going to introduce actually a third quantum number. So n tells me which energy level I'm in, L tells me which set I'm in, and now I'm going to introduce yet another quantum number. And it's going to be called the magnetic quantum number. And my magnetic quantum number is going to be given the symbol lowercase m with a subscript of L underneath it. Okay, so this is the magnetic quantum number. And really what I'm going to use this magnetic quantum number for is as a labeling system for each of my L sets. Okay, and again, you're kind of sitting there going, wow, there's a lot of numbers here. This is getting a little bit confusing. I just want to stress that this is really literally just a labeling system. And it's going to be the final element of our pattern in numbers so far. Now, this magnetic quantum number, m sub L, is well defined for every value of L. Okay, so when L is 0, my magnetic quantum number is 0. So I can indicate that, and I'm just going to indicate that with a small number above each of the states, and I'm going to keep my colors consistent here so that we can see that. There isn't a lot of point, I agree, to those zeros that I just wrote, because there wasn't several orbitals with L equals 0 or several states with L equals 0 to label, but I'm going to be explicit about this, and I'm going to actually use my ML all the time. And the rule, the way ML is defined, is you go to the middle state in your set, and there always will be a middle state, because if you recall earlier, the pattern is we always add an odd number of states, so there's always a middle one. You go to the middle one and you label that middle one with a 0. Okay, so we can do that every time. We label that middle one with a 0. And what we can do after that is go past 0 in both the positive and the negative direction. And you go past 0 in both the positive and negative direction as far as you need to go to assign a label to all of these different states. So if I look at this L equals 1 set of states, if I go to the right, I will be at +1. And of course it is identical in both instances here. And if I go to the left, it's probably not surprising, I will be at -1. And so now I actually have a way to label each and every single one of these states. So if I go over here to this L equals 2 set of 5 states, I can play the exact same game I just played. And now I would label the first one as +1, the second one beyond the middle as +2. Likewise, I would go in the negative direction, and there we are. I've just labeled all of these states. And I needed 3 numbers to do it. You could almost consider these numbers I'm using as coordinates, literal, coordinates, like an address, for example. So I could specify for you, if I chose, I could write a set of numbers as n, L, m sub L. And if I write out that set of numbers, I can essentially point to any one of the states I've written. And in fact, I could point to any one of the states that I haven't even written yet, because now you know the pattern. You could go up to n equals 4 and write 16 things across and group them as the first one goes by itself, then the next 3, then the next 5, then the next 7. And you would know that the 7, the group of 7, would have an L value of 3 because it must be 1 greater than the set before it. And you would know how to label all of those in terms of M sub L's, because the middle one would get 0. And you would go 1, 2, 3 to the right, and then -1, -2, -3 to the left, so on and so forth. This pattern could go on forever. It doesn't matter. Now that you understand the pattern, all I need to do is specify these 3 numbers, and you know exactly what I'm talking about. So for example, if I were to say, give you the set of numbers 3, 2, -1, I could say, hey everyone, does this 3, 2, -1, does that make any sense? Is that a valid quantum set of numbers? Is that a valid set of numbers that defines a quantum state of my system? And you would say to yourself, well, let's see, n equals 3, there's n equals 3, L equals 2, yeah, so that exists. There is an L equals 2 for an n equals 3, right? That does exist. Notice that there isn't an L equals 2 when n equals 2. that state wouldn't even exist. That would be an invalid set of numbers. That would be an address that points nowhere. But 3, then 2 makes perfect sense, and then -1. So we're talking about this particular energy state with this particular set of numbers. Okay, so we have an address system, and it works. And there's a pattern embedded right inside of it, right? So you can see that pattern for yourself. We've already talked about the n squared bit, right? So there are n squared states for every value of n, okay? There are also n minus 1 values of L. Now let me explain that. So if I'm n minus 1 would be 1 minus 1. That would be 0. Notice that is the maximum value for L in this row. I can do the same thing as I go up to any row. If I go up here, n equals 2. Well, n minus 1 is 2 minus 1. That's 1. And notice 1 is, in fact, the maximum value for L here. Same thing, n equals 3. N minus 1 is 3 minus 1 or 2. 2 is the maximum value of L. So we do have a max here if we want to specify it as such. And the maximum value for L happens to be n minus 1. Okay, so if we ever have an L value that is greater than n minus 1, it doesn't make a lot of sense. It doesn't exist in our little pattern system that we've got here. And likewise, our pattern for m sub L is potentially obvious at this point. It's whatever the L value is, you go from the positive of that number to the negative of that number, right? So if my L value is 2, then my m sub L values go from -2 all the way up to +2. And the way we write that, the way we would indicate that here, using some notation here, we would say that ml runs from -L all the way to, and I go ... to 0 all the way to +L, right? So that's the range that my m sub L, or magnetic quantum number, runs through. Okay, so these are all the patterns, and you know, I agree this is complex. There's a lot of different states here, but all of those different states explain the complexity of the barcodes that we see in all the different atoms in the periodic table. And as we excite them, they emit very specific photons, and we have very specific wavelengths of light that are given off. But hold on a second. Now I've just introduced yet another complication. This actually doesn't yet explain all of the other elements from hydrogen. There is a final piece that I've not yet sorted out for us. If it's true that all of the other elements in the periodic table emit barcodes that contain different numbers of photons, different numbers of spectral lines, and those different lines are in different places, they have different energies, then we've not quite reconciled that yet, because the image I'm showing you now is really just an elaborate picture of the hydrogen atom, isn't it? I mean, don't we have only states at this particular energy right here, and at this particular energy, and at this particular energy? In other words, aren't the deltas exactly the same as they always were, right? The changes. Isn't it true that in the diagram I'm showing you right now, isn't the difference in energy between n equals 3 and n equals 2 exactly the same as it was in the old diagram I just drew? All of this complexity, these n squared states at every level of n, doesn't change the energy, nor does it change the difference between any two states. So we've not quite sorted it out. We've got a lot more states, and therefore we've got a lot more options, but they seem to be just as far apart as they were for the hydrogen atom. Therefore, it seems to be that we're proposing that my electron can still only jump back and forth between the same energetic places. And that's not going to explain different barcodes. That's not going to explain atoms other than hydrogen, okay? And so this is still going to falter a little bit. It's still going to have some of those Bohr problems. So what is the final change we need to make? Well, the final change we need to make is the realization that for multi-electron systems, right, for systems that are not hydrogen, you add a second electron. So, right, so maybe you've got, hydrogen minus, and so it's got an extra electron. Or maybe you've got helium, or lithium, or carbon, or iron, or any of the other elements of the periodic table with many electrons in them. What happens is the energy of these various states start to change, okay? And thankfully for all of us, they change in, you guessed it, a pattern. And let me indicate that for you here in my diagram. Schematically, what happens is the L values begin to rise in energy. And so what I mean by this is, what happens is when I have a set of energy states that have an L equals 0 and an L equals 1, like we do here at the N equals 2 stage, what happens is my L equals 1 states tend to be higher in energy than my L equals 0 state. In other words, the L equals 1 states begin to separate from the L equals 0 states. That's what happens. Likewise, the L equals 2 states begin to separate from the L equals 1 states. There is a stratification, if you will, of these states as I add more and more electrons to my system, and consequently more and more protons in the nucleus of these atoms. These states become more and more stratified. They start separating from each other more and more. So what we see is that the N equals 3 states with the L equals 2 states separate and get raised quite a bit relative to the others. Likewise, the L equals 1 states of that same set raise as well relative to the L equals 0 ones, and we get this stratification I was talking about earlier. And this happens for all principal quantum numbers. So for the N equals 2 level, we get a bit of separation as seen here. For the N equals 3 level, we get that much more separation, and then that much more separation again. And this would be a very, very complicated picture if we were to just draw these black lines all over the place and just indicate them on this axis as a bunch of lines. We would just be, hopelessly lost in terms of seeing any pattern underlying this. But when we start out realizing that these are grouped in sets, and we add these groups in a very systematic way as we go to higher and higher N values, we begin to, I think, see that pattern far more clearly. And so now what we have is a picture where we have many states that are at this energy, many states that are at this energy, and this one, and these, and this one, and this one. And notice we've got a whole plethora of new states to choose from. Therefore, we've got all of these new places for electrons to go and new amounts of energy for electrons to absorb, right? Electrons can now absorb just this small little amount of energy, the difference between this state and this state. There was no option to absorb that particularly small amount of energy before. Now there is. And so likewise, it can also emit that particularly small amount of energy. And so as we go to larger atoms with more electrons, with more stratification in all of these different energy states, we have more complicated barcodes where we get all kinds of different colors of photons and many more photon types than just in the simple hydrogen atom itself. And so while the hydrogen atom was a beautiful example of quantization, which tells us that these energy states exist, which is the heart of quantum mechanics, as you go to more complicated atoms, you get far more complicated barcodes, but it is all based fundamentally on what can be understood as a relatively simple pattern. It just gives us a lot of states, and a lot of states give us a lot of energetic options, which gives us a lot of lines in our barcode, quite frankly. And so this is where Schrodinger's model excels. It allows for this kinds of flexibility to describe really any atom in the periodic table, and likewise, as we'll see in future classes coming up next month, any molecule or substance that exists in the universe. Okay, just to wrap up this system of an address, if you will, there's just a couple sort of final details before we talk about, what this all means, and what do each of these energy states actually look like, and what does it mean to be in one of those states. The Bohr model thought about orbits, which were really just circles, right? It was a planetary model. It was just like the Earth going around the sun. The Bohr model thought maybe an electron orbits around a nucleus. And so Bohr, in his states, which remember the Bohr states would have just been these ones right here. In the Bohr states, they were called orbits. In the Schrödinger states, which is the ones we're talking about here, the more accurate states, the more realistic states, we got away from that prescriptive path of just, this circular path going around a nucleus. And instead, we started to talk about three-dimensional space, which is far more realistic. And so instead of saying an electron goes around in a circle around the nucleus, what we actually start to say instead of that is that the electron occupies a three-dimensional space in the vicinity of the nucleus. And this three-dimensional space in the vicinity of the nucleus is what we call an orbital. Okay, so an orbital is a term that you might have heard of before, not to be confused with orbit, which is again what the Earth looks like when it goes around the sun. An orbital, or an orbital, is really as I said before, a three-dimensional region of space that we say we expect to find a particle in. And so each of these energy states, each and every single one of them, can all be referred to as an orbital. They define a state, and when you are an electron and you go into an excited state, you change your distribution. In the Bohr model, that supposition was that you would just be in a bigger orbit. So if you had more energy, you would be orbiting the nucleus in a wider radius. That's how you handled that increase in energy. In the Schrödinger model, we have something analogous, which is different three-dimensional regions of space that we occupy when we are differently energized, if you will. So there's a ground state distribution, there's a ground state space that I live in, and then if I get excited, I might occupy more space. I might be, whizzing around the nucleus that much quicker, and I might be likely to be in a larger region of space. And so that's what all of these states or orbitals actually correspond to. And so I want to take a look at those orbitals. But the first thing I want to do before we just take a look at those orbitals and what do each of these states correspond to is I just want to introduce the final piece of notation that allows us to describe these. And that is the letter typically associated with these L values. Okay, so now this is something I've not necessarily explicitly discussed yet. But each of these L values, this value of 0, value of 1, value of 2, while perfectly valid and fine and complete, we often supplement it with a letter, okay, for reasons that are purely historical. They come from interpreting those barcodes I talked about before. And once we replaced the words that described those barcodes with these proper addresses and numbers and numerical indices of what all those different barcodes corresponded to, those letters tended to hang around, and they're still ubiquitous in the language of chemistry right now. So what are they? Every time you have a 0, an L value of 0, you have what is called an S state or an S orbital. So likewise, all of these zeros are S orbitals or S states. Now, when you have a L value of 1, you have what are called P orbitals or P states. When you have values of 2 for your angular momentum or azimuthal quantum number, you have what is known as a D state. And although I have none on my diagram right now, if I were to have had and an orbital value or an angular momentum quantum number value of 3, these would be called F states. And if you care, it goes up past this, and you start talking about G, and then H, I, J. You follow the alphabet after that. You don't start with the alphabet. Again, these are hangovers from historical interpretations of these spectra. But you go S, P, D, F, and then it's G, H, I, J all the way through the alphabet after that. But I promise you will never have to go there. The vast majority of chemistry, almost every atom in your entire body, can be described with the states that are on your screen right now. This is a fairly complete discussion of orbitals and energy states available to most of the atoms you would ever interact with. So this is a fairly complete discussion, and so S states, P states, D states, and F states occasionally are fairly complete. Okay, so I can then talk about say a 3D orbital, for example. And what is a 3D orbital? A 3D orbital is one of these, because the notation, the language I would use, I would say you would use your principal quantum number first. So I would say 3D. So there's such thing as a 3D orbital. There's no such thing as a 2D orbital. They don't exist, right? Because that's a violation of those patterns I was talking about earlier. Likewise, there's no 1D orbital, but there is a 1s orbital. And in fact, the 1s orbital, or the 1s state, is our ground state. It's the lowest energy state on this whole diagram. We also have a 2s state right here. 2p, right? This is a set of 2p states. I have a set of 3p states, and I have a set of 3d states. Okay, so that is, as I said before, ubiquitous language in chemistry. You'll hear it all the time. And so now we know that the Bohr model was wrong. It doesn't explain multi-electron systems. What we need to do is go to Schrödinger, who expanded the math on all this stuff and actually discovered that there were many more states. There is a beautiful pattern embedded in where these states come from. It's a mathematical pattern. The magic in this, though, is that nature adheres to this pattern, and we can predict all of those barcodes and those spectral lines that you observe based on where electrons are in our system and what states those electrons are in, and our electrons have all these choices for states. So there are many choices, therefore many different jumps and falls that can happen between these states, and therefore more complex barcodes. And we developed a labeling system here. This labeling system is a set of quantum numbers, a principal quantum number n, an angular momentum quantum number L, and then a magnetic quantum number M, which defines in a numerical way an address for all of these different orbitals or all of these different energy states. And it's just common for us to use these letters to indicate the value of the angular momentum quantum number instead of the numbers. And so the phrase 2p orbital will be a very common one that you should be familiar with. Now, what we're going to do in this next part is we are going to take a look at these states and try to understand what they're telling us and what they mean.